What specific problem does your proposed method, GOAT, aim to solve in the context of adversarial testing of large language models?
The proposed method, GOAT, Generative Offensive Agent Tester, aims to solve the problem of effectively automating adversarial testing of large language models, LLMs, in multi-turn conversational settings. Traditional approaches have primarily focused on single adversarial prompts, which overlook the dynamic nature of user interactions where multiple queries and techniques are employed in a conversation. GOAT addresses this by simulating human-like red teaming, allowing the attacker LLM to adapt its strategies based on the target model's responses throughout the conversation. This method not only enhances the attack's success rate, but also reduces the number of queries needed to elicit unsafe responses, achieving high effectiveness within a limited conversational budget. By integrating various jailbreaking techniques and reasoning through the conversation, GOAT provides a more comprehensive and efficient framework for testing LLM safety.
How does the GOAT method work? Illustrate the process step by step, detailing the main components and their functions in the adversarial conversation.
The GOAT method, or Generative Offensive Agent Tester, operates through a structured process that simulates adversarial conversations with a target language model, LLM. First, it initializes an attacker LLM with red teaming instructions and a set of predefined adversarial attack strategies, which can be applied individually or in combination. The attacker LLM then generates an initial prompt based on a specific adversarial goal, which is sent to the target LLM to elicit a response. Following this, the attacker LLM analyzes the target's response, reflecting on the conversation's direction and strategizing the next attack, which is informed by the previous interactions. This cycle continues for a maximum of 5 conversational turns, allowing the attacker to dynamically adapt its approach based on the target's responses, thereby effectively navigating around the model's safety mechanisms to achieve the desired outcome.
Can you provide a simple example illustrating how GOAT conducts a multi-turn adversarial conversation with a target LLM? Please detail the sequence of interactions that demonstrate its techniques.
In a multi-turn adversarial conversation, GOAT begins by establishing a hypothetical context to subtly guide the target LLM towards a violating response. For instance, it might initiate the conversation by asking the target to role-play a fictional character in a scenario where the Nazi Party has won the war, without directly mentioning any unsafe terms. As the conversation progresses, GOAT observes the target's responses and identifies that the output lacks the desired level of violation. It then escalates the conversation by applying response priming, asking for a description of the New World Order and the benefits it brings, which further nudges the target LLM towards a more violating output. Throughout this interaction, GOAT dynamically adjusts its strategies based on the target's replies, effectively employing techniques like hypothetical framing and response priming to achieve its adversarial goal. This illustrates GOAT's capability to adapt and escalate the conversation, similar to a human red teamer.
What are the main advantages of using GOAT compared to existing adversarial prompting methods? How do these advantages manifest in terms of attack success rate or efficiency?
The main advantages of using the Generative Offensive Agent Tester, GOAT, compared to existing adversarial prompting methods include its high attack success rate, efficiency in query usage, and dynamic adaptability in multi-turn conversations. GOAT achieves an attack success rate (OSR) of 97% against Llama 3, 1 and 88% against GPT-4 Turbo, significantly outperforming the earlier method, Crescendo, which requires more conversation turns to reach peak performance. Additionally, GOAT operates effectively within a limited budget of just 5 conversational turns, achieving high success rates with fewer queries, as it does not require a separate judge model during the conversation. This efficiency is further enhanced by the attacker LLM's ability to reason through responses and adjust strategies dynamically, allowing it to sidestep safety measures more effectively than static single-turn approaches. Overall, GOAT's design allows for a more nuanced and effective adversarial probing of language models, leveraging multi-turn interactions to maximize the likelihood of eliciting unsafe responses.
How did you validate the effectiveness of GOAT, and what specific metrics were used to measure its performance? Please describe the experimental design and datasets involved in the validation process.
The effectiveness of GOAT was validated through a series of experiments using the Jailbreak Bench dataset, which consists of 100 behaviors soliciting harmful responses from language models. The experimental design involved initiating multiple conversations between the GOAT agent and various target models, including Llama 3, 1 and GPT-4, with a maximum of 5 conversational turns per interaction. The primary metric used to measure performance was the attack success rate, ASR, specifically ASR at 1-0, which indicates the proportion of conversations that produced at least one unsafe response deemed violating by a judge model. Additionally, the evaluation was conducted using a scoring setup that involved a judge model to assess the outputs of the target LLMs, ensuring reproducibility and consistency in the results. GOAT's performance was compared against the crescendo method, demonstrating higher ASR rates and fewer required queries, thus highlighting its efficiency in multi-turn adversarial settings.
What limitations or drawbacks did you identify in GOAT's approach, and how might these affect its applicability or performance in real-world scenarios?
The paper does not explicitly outline limitations or drawbacks of the GOAT approach. However, some potential concerns can be inferred. Firstly, while GOAT achieves high attack success rates, it relies on a predefined set of adversarial techniques, which may limit its adaptability to novel or unforeseen model defenses in real-world scenarios. Additionally, the effectiveness of GOAT is contingent on the attacker LLM's ability to reason and adapt dynamically, which could be hindered by the inherent unpredictability of language model responses. Furthermore, the reliance on multi-turn conversations may introduce complexity, as longer interactions could lead to increased chances of detection or intervention by safety mechanisms. Lastly, the paper notes that GOAT does not require a separate judge model during the conversation, which could raise concerns about the accuracy of evaluating success in real time, potentially affecting the reliability of its outputs.